Okay, AP Chem. So we have just a couple more topics to cover in chapter 11. One of them is the very last colligative property, which is osmosis. So I want you, before we start talking about this, I want you to think of a scenario. If I have two beakers of solution, let's say they're both 1 liter. And let's say the first one is 2 molar NaCl, and the second one is going to be 1 molar NaCl. Okay, so we have these two beakers. Now, I'm going to connect these two beakers. Let's say these two beakers are connected by a semi-permeable membrane. A semi-permeable membrane is going to allow water to pass through, but not the sodium or chloride ions. So if this is the case, toward which beaker will the water flow? I want you to pause this video and think about that until you have a decision, and then come back to us. So hopefully you recognize that this is the very definition of osmosis. Water flowing when solute cannot flow. That is the definition of osmosis. And water is always going to flow towards the side with a higher concentration until the two concentrations are equal. And so our water in this scenario is going to flow toward the left, and it's going to fill up, hopefully, a larger beaker, until the concentration of the two beakers is equal. So this is osmosis. It always occurs water flow will occur toward the side of higher concentration until the concentrations are equal. You can see down here in the picture, if these are equal volume containers, you can see this is the same scenario. So I have like maybe a 6 molar solute concentration on this side, a 2 molar concentration on this side. Solvent, my water, is going to flow toward the higher concentration until the two concentrations are equal. So the question is, how much pressure does it take to stop this? And that's what osmotic pressure is. So if we look at this scenario up here, I have like a U-shaped tube up here. You can see I have a semi-permeable membrane in the middle. I have solute on one side, and then I have no solute on the other side. So same scenario, this water is going to flow from the right to the left, from the area of low concentration to the area of high concentration. This water level is going to drop, and this water level is going to rise. Now, osmotic pressure is going to be if we tried to stop this flow. So let's say we put a piston here, and in our little piston, this is supposed to be a piston-shaped item. There, that's looking a little bit better. Okay, so if we had a piston here and we pushed down with some force onto our piston, how much force would we need to use in order to stop the flow of water in this scenario? That would be osmotic pressure. Okay, so let's take a look at the formula for osmotic pressure and kind of break this concept down a little bit. So first of all, note that osmotic pressure is pi, right? I love this. It gives us a second use for that awesome symbol. Notice here, pi represents osmotic pressure, which can be any number. Okay, it does not represent 3.14 in this scenario. Okay, the second thing we notice is that it uses the Van Hoff factor. So pi, or osmotic pressure, equals IMRT. So I is going to be the Van Hoff factor. This is a colligative property. It does depend on how much is present, not what is present. So This is going to depend on the number of ions present. And if molarity is calculated in terms of the compound, then you must use I to compensate for that compound breaking into ions. Okay, notice that it does contain M, it does contain molarity. So like all the other colligative properties, osmotic pressure is going to be dependent on concentration. The number matters, not necessarily the thing that's dissolved. R is just a constant that makes it work. It's a very specific constant. It's called the ideal gas law constant. The number is right there, 0.0821 liter atmospheres per mole Kelvin. This number is on your reference sheet. It might be a good time to go find it on your reference sheet. And then again, osmotic pressure, like a lot of the other colligative properties, is going to be dependent on temperature. But this dependence on temperature is actually incorporated into the formula, which is why R doesn't change like K does in the other examples. Okay, so this is osmotic pressure. It's the pressure required to stop the flow of water from low concentration into high concentration. Just a couple context terms to know about. Isotonic, hypotonic, and hypertonic. If you have taken any of the med terminology classes, you've probably run across these terms. Notice that they're iso, hypo, and hyper. So iso means the same. Hypo means low, hyper means high, and then tonic is always referring to a concentration. So isotonic solutions would be where the two solutions are the same concentration. Hypotonic is where your subject is at a lower concentration than whatever it's being compared to, usually the surroundings. And then hypertonic, again, your subject is at a higher concentration than whatever you're comparing it to. Usually it's surroundings. So the biological application of this is usually when we're talking about red blood cells, because red blood cells are semi-permeable, just like those semi-permeable membranes we were just talking about. Red blood cells will let certain things through, but not other things. And most of what we're talking about is water. So red blood cells will support the flow of water in or out of the red blood cell based on the concentration of the red blood cell compared to whatever it is around. So when the red blood cell is at a lower concentration than the solution around it, we would call the solution a hypertonic solution. The solution is at a really high concentration. The red blood cell is at a really low concentration. So again, we're going to see this flow of water from low to high concentration. The water is going to flow out of this cell and it ends up shriveling. The red blood cell actually shrivels, and we call this crenation. That's your med terminology word of the day. The opposite will also happen if we take a red blood cell and we put it in solution that is at a really low concentration. Water will flow in from low to high. It'll flow into the cell, and the cell can stretch and stretch and stretch to some extent. But if it keeps stretching, it will eventually break or rupture. We call this hemolysis. So hemo means blood. Lysis means like a splitting or a rupturing. And the blood cells will actually break open, which is a really bad scenario. You definitely don't want this happening. The red blood cells will die. And if it's allowed to occur to a great enough extent, the patient will also die. So this is a good example of why we put, if you ever severely dehydrated and you get admitted to the hospital, what they'll do is they'll put a needle in your arm and they'll run a saline drip into your arm. Well, this is why they put saline into you, which is basically salt water. They don't put fresh water into you, because if they put fresh water into you, then all of a sudden your blood would be at a lower concentration. It would be a hypotonic solution when compared to your red blood cells, and all your red blood cells would start rupturing, which would be a really bad scenario. That would not be helpful to your patient at all. If they put a saline solution in you, then it may be slightly hypotonic compared to your blood. It may be slightly hypertonic compared to your blood, but it's not actually going to cause the red blood cells to burst open. Fun facts about your blood. You're welcome. Okay, so the Van't Hoff factor, let's talk about this for a little bit. The Van't Hoff factor, we've been dealing with it as if it's an ideal solution. So whenever you hear this term ideal, what you want to think of is if it's an ideal solution, then the model is perfectly right. Okay, so usually we make all these models and equations in chemistry, and they have to be tweaked and added down the line, but they give us a good enough predictor of what's going to happen that they're useful to us. Well, the Van't Hoff factor is exactly like this. It's not like NaCl does not exactly split into Na plus and Cl minus. It doesn't completely do that. Right? It may completely do that under specific circumstances, but if you go towards extremes in your circumstances, usually your models, they act less ideal. And so in that case, the Van't Hoff factor gives us a pretty good estimate of what's going to happen, but you have to keep in mind that when you approach extremes in the conditions, any model is going to break down and not be quite as useful or close to the actual behavior of the solution as we might expect it to be. And here's why the Van't Hoff factor does not act ideal all the time. Because NaCl, Na plus and Cl minus, while they dissolve in water, they're constantly moving, just like the liquid is constantly moving. And eventually they're going to run into each other. And when they run into each other, they do attract each other. And so if they collide, they might stick together for a moment before they get broken up and flow around again. And the more of this electrostatic interaction that you get between the positives and the negatives on your ions, or the partial positives and the partial negatives of your polar molecules, the less ideal something is going to act. So try to think about a couple circumstances. What could we do to a solution to make the condition extreme so that these electrostatic attractions start happening more and more? And one way we could do this is by increasing the concentration. If you have a super saturated solution, you're going to have lots and lots of ions very close together, and the chances of them hitting each other and momentarily sticking and acting like one particle instead of two particles is much higher. And at that point in time, your Van't Hoff factor would probably be less than 2, since they're momentarily sticking together and acting like one molecule. If you dilute it, add lots of water, and you take these ions and move them really far away from each other, they're going to act more ideal. A similar circumstance happens as you get ions that are highly charged. So like aluminum would be a highly charged ion compared to sodium. So if instead of putting sodium chloride into your solution, you had aluminum chloride, or like aluminum phosphide for that matter, okay, these ions are going to attract each other even more across greater distances and probably stick for longer periods of time and act less ideal. The lower you go in charge, the more ideal your solution is going to be, which again is why we do so much with sodium chloride. It's cheap, it's safe, and it acts super, super ideal. And so it makes it the perfect example for a lot of these things. All right, here's a couple practice problems for us to touch base about. Colloids. So this is our last discussion point for solutions. When you're looking at solutions, so far we've really talked about solutions that contain ions, and that would be this last column here at the bottom. So salt in water, any salt in water would fall under this category. When salt gets dissolved into water, it breaks into these little particles that are about the size of molecules. If you let this solution sit for years, gravity will have no effect on it. It'll never pull these particles out of solution. The interaction between the particle and the water is greater than the interaction between the particle and gravity. So gravity can't pull it out. If you pour it through a filter, the ions are just going to go through the filter with the water. So the filter cannot separate these things out from each other. And then here's our next test, shining a light through the solution. So these ions are so small that they're too small to actually reflect light. So as you shine a light through a solution, you're not going to see anything. They're not big enough to actually scatter that light. Okay, so we're going to compare this to something that we call a colloid. So a colloid is a particle that's just a little bit bigger than a molecule. And we'll talk about a couple examples, and it's really fun to go around your house and find examples of these for yourself. They exist in your house. I guarantee you they do. Again, colloids are too small, so gravity is not going to have an effect on them. If you let them sit for ages, they're going to be dispersed exactly the same because their interaction with water is greater than the pull of gravity on them. If you pour them through a filter, you can't separate them out. They are too small. They are still close to the size of a water molecule, and so they will go through the filter with your water. But if you shine light through this substance, the things in solution are just big enough that it will actually scatter the light. So let me show you what I'm talking about. This is called the Tyndall effect. So look at this example right here. Here, notice that we have a light that's shining through both solutions. The yellow solution, whatever's dissolved in there, probably ions, is too small, so you don't actually see any light being scattered. You can't see the beam of light in it. But this second solution, the red solution, whatever's dissolved in there, is slightly bigger, and so it scatters the light, and what you see the beam of light through the solution. So that is evidence that you have a colloid in that solution, and that's what we call the Tyndall effect. You may have seen the Tyndall effect outside too, if you've ever seen a beam of light coming through like the window in your house or trees in a forest. That's the Tyndall effect. There's something in the air. There are particles in the air that are big enough to scatter the light, and so you see the beams of light that are coming through and being scattered by those particles. Now, there is one more size that we should talk about, and a good example of this is clay in water. And some of those particles in the forest that are scattering light could fall under this category also. So clay particles tend to be very large particles. Same thing with like ash in the air tends to be fairly large particles. If you give it enough time, these particles will separate out. The interaction between the particle and gravity is stronger than the interaction between the particle and water, and eventually gravity will pull these things out of solution. A filter will separate them out. So if you pour clay mixed with water through a filter, you'll be left with the clay on the top and the water will come through. Same thing with our precipitates that we formed in lab. The precipitate will stay on the filter. The water will come through. And these particles are so big, they may scatter the light if they're far enough apart, like ash is sometimes in the air. But a lot of times they'll just block the light. The light won't get through at all because it'll just be blocked by these rather large particles. Particles can be gas, liquid, or solid. and they can be dispersed in gas, liquid, or solid. So we think of solutions as liquid a lot, but solutions can also be made with solids floating through the air. That would be a solid gas combination. They can be gas dissolved in liquids like the soda we talked about. There's a lot of different combinations that can happen and can form solutions for you. Here's some more examples of the Tyndall effect. This one's pretty dramatic. Both substances look very clear, but one clearly scatters light while the other one doesn't. So this one on the left is exhibiting the Tyndall effect and is indeed a colloid. Okay, colloid removal, since you can't use gravity to pull it out, you can't use a filter to pull it out. There are methods of colloid removal, and we call them coagulation. So getting these particles to stick together to be a big enough particle then that gravity could pull it out or we could filter it out is usually the method that we go through. For example, smoke in stacks. A lot of times smoke is like scrubbed as it goes through the stack. And what that action is they actually attach particles to the gas that's being produced in the smokestack or the solid that's being blown through the smokestack. They'll actually attach it to something bigger, and then that can be filtered out, or we can use gravimetric analysis to pull it out. Another really good example is the butterfat in milk. If you've ever tried to heat milk, you'll notice that the milk tends to coagulate and stick together. If you do it in a cup, you may get this like layer on top of the milk that's not really delicious. Or if you do it in a pan, this is how cheese is made. They heat the milk, and then the milk proteins start to stick together. Or you can stirring. So heating can do it. Stirring can do it. If you put cream in a blender and just put it on high for like 3 minutes, all of the proteins or the fat, I guess, in the milk will start to stick together. And that's what you get as butter, is all you're coagulating these little things inside the milk. Electrolytes can do this. They can attract the particles. They can neutralize surface charges, and then they can disrupt the electrostatic attraction with the water and get it to settle out. Dialysis is also used as these solutions are kind of forced through very, very specific semi-permeable membranes, like in kidney dialysis, where they've kind of flush the blood through these semi-permeable membranes and pull some of these things out of blood that we consider to be toxic waste inside our body that we need to be removed from our blood. So there are ways to get colloids out. It's just a little bit more difficult.